Have you ever just stopped and wondered why things only seem to happen in one direction? I mean, why the universe seems to have this built-in one-way street for, well, for everything. Today, we're going to figure that out.
Let's kick things off with something super simple, something you see every single day. You pour a hot cup of coffee, you put it on your desk, and what happens? It gets cold, always. Heat flows out of the coffee and into the cooler room. But have you ever seen a lukewarm coffee on your desk just start steaming all on its own? No way. And that simple observation right there is the key to this huge scientific idea: spontaneity. And it's not just our coffee, right? Nature is absolutely full of these one-way streets. A shiny new nail gets left out in the rain, it rusts. You'd never see a pile of rust magically turn back into a nail. Water flows downhill. A single drop of food coloring clouds up a whole glass of water. And we all know this one: a clean room will, over time, get messy all by itself. All of these are what scientists call spontaneous processes.
Okay, so to really get this, we have to be super clear about what that word spontaneous actually means, at least in science. It's not what you might think. It doesn't mean something happens in an instant or for no reason at all. Nope, it's got a much more specific and honestly a much more powerful meaning.
Here is the absolute key distinction you have to get. Spontaneous is all about the direction a process wants to go, not how fast it gets there. A spontaneous process is just something that will happen on its own without you having to constantly push it along. But here's the kicker. It could be lightning fast, or it could be unbelievably, ridiculously slow.
Get this. That beautiful diamond on a ring? It is spontaneously turning into graphite. Yeah, the same stuff that's in your pencil lead. It's a spontaneous process. The thing is, it's so incredibly slow, we're talking billions of years, that we don't have to worry about it. It's the perfect example. Spontaneity is about the destination, the direction it's headed, not the speed of the journey.
Okay, so if it's not about speed, what is the actual driving force here? What's making these things want to happen? Now, the first guess for most of us is that things just want to get to a lower energy state, like a ball rolling to the bottom of a hill. And that's part of the story, for sure. But it's not the whole story, not even close. Check out this classic example. Picture a box with a divider down the middle. On one side, you've got a bunch of gas. On the other side, a perfect vacuum, just empty space. You pull out the divider. What happens? Whoosh! The gas instantly expands to fill the entire box. Every single time. But here's the thing. The total energy of the gas didn't change at all. So the driving force wasn't a loss of energy. It was something else. It was the dispersal of matter. The gas just spread out. This deep, fundamental tendency for things, for matter, for energy to just spread out has a name, and is probably one of the most famous and maybe one of the most misunderstood concepts in all of science. It's time to meet entropy.
So what on earth is entropy? Well, at its heart, it's a measure of dispersal. You'll often hear it called a measure of disorder, and that's a pretty good way to think about it. But if you want to be really precise, it's a count of all the different possible ways the tiny particles and energy in a system can be arranged. We call those microstates. The more possible arrangements, the higher the entropy.
Let's make this really concrete. Imagine you just bought a brand new deck of cards. It's perfect, right? Every suit is in order, ace to king. That is a very specific, highly ordered arrangement. There's basically only one way for it to be that perfect. That, my friends, is a low entropy state. Very few ways to arrange it. Now take that perfect deck of cards and just throw them up in the air. How are they going to land? In a complete mess, a jumbled pile. Now think about this. How many different ways can those cards be arranged in a messy pile? A staggering number. Trillions and trillions. That is a high entropy state. And nature favors high entropy for a very simple reason. It's just statistically way more likely. There are just so many more ways to be messy than to be neat.
So this preference for things to get more spread out, more disordered, it's not just some casual suggestion. It's a fundamental law of the universe, just as real as gravity. In fact, it's a law that gives time its arrow. It's the reason our coffee gets cold.
And here it is, the big one. The second law of thermodynamics. It says that for any spontaneous process, anything that happens on its own, the total entropy of the entire universe has to go up. The whole universe is always and forever getting more and more disordered.
Okay, but hold on. This is where it gets really interesting. Because if the universe is on this unstoppable slide towards maximum messiness,
how do we explain things that get more ordered? How does any kind of structure exist at all?
I mean, just think about water freezing. You have these liquid water molecules just tumbling around randomly, and then as it gets cold, they spontaneously snap into place, forming a beautiful, perfect, highly ordered crystal of ice. The entropy of the water itself clearly went down. It got more orderly. This looks like it's breaking the second law. So, what is going on here?
And it's not just ice either. You see this everywhere. Soap molecules in water will just arrange themselves into these complex little spheres. And of course, life itself is probably the most breathtaking example of spontaneous ordering there is. So there's definitely a piece of this puzzle that we're missing. To solve this puzzle, to figure out this paradox, we need to introduce a new idea. It's the final judge, the ultimate decider of what's spontaneous and what's not. It perfectly balances the universe's competing desires, the drive for lower energy and the drive for higher disorder. Let's meet Gibbs free energy. We just call it G for short. It's named after an incredible American scientist, Josiah Willard Gibbs, and it's the master key we've been looking for. It cleverly combines the two big driving forces we've been talking about, enthalpy, which has to do with heat, and our old friend, entropy, the measure of disorder. And here it is, the legendary equation that puts it all together. The change in Gibbs free energy, that's delta G, equals the change in heat, delta H, minus the temperature times the change in entropy, delta S. This equation is the ultimate decider. It's a tug of war between the tendency to release heat and the tendency to create more disorder. And the rule could not be simpler. All we care about is the sign of that delta G. If it comes out negative, nature says go. The process is spontaneous. If delta G is positive, it's a no-go, it's non-spontaneous. And if it's zero, well, everything's in balance. Okay, let's go back and solve our ice puzzle. Take a look at that third row. When water freezes, it releases heat, so delta H is negative. And we know it gets more ordered, so delta S is also negative. Now look at the equation. At a low temperature, that little t is a small number. That means the negative delta H term is the boss. It wins the tug of war, making the final delta G negative. And boom, that's why water spontaneously freezes when it's cold.
But what happens when you warm things up? As the temperature T gets bigger, that T delta S part of the equation gets much more powerful. Eventually, it becomes more important than the heat term. For freezing, delta G flips and becomes positive, but for the reverse process, melting, delta G becomes negative. And so, at room temperature, ice spontaneously melts. It's all just this beautiful, elegant balancing act with temperature as the referee.
And that brings us to one last, absolutely mind-bending thought. Life. We are the ultimate examples of spontaneous order. Your body is this unbelievably complex, highly ordered machine, and it doesn't break the second law for a second. In order to build and maintain its own incredible order, a living thing has to constantly take in energy and create an even greater amount of disorder in its surroundings by releasing heat, by breaking down food into simple molecules. We are, all of us, these little islands of order that we build by making the universal ocean of chaos just a little bit bigger. So what does that tell you about our own fleeting, improbable, and beautiful existence?